We're going to begin this segment with a prerequisite skill. Okay, so I actually want you to begin by pausing the video, and you're working with this right triangle, and you want to express C in terms of A and B for the first one. And then for number two, try to recall the distance formula that you learned back in high school. So pause the video and give these two a try. Okay, if you're back, we all know that a squared plus b squared equals c squared. All right, Pythagorean theorem, we all know that. And therefore, if you want to solve for c, right, we would take the square root of both sides. And normally when we take the square root of both sides, we need to consider plus or minus. But since we're talking about lengths of sides of triangles, we don't have negative lengths. All right, so that's why we neglect the plus or minus thing when we're working with the Pythagorean theorem. Okay, and so what I want you to notice is that the length of the hypotenuse, all right, is equal to the square root of the sum of the legs squared. Okay, that's going to be useful to us in a few minutes. And then over here for distance formula, distance is equal to the square root of the difference in the x coordinates. All right, so you either can write x sub 2 minus x sub 1, or sometimes you write like x naught minus x sub 1, plus sometimes students have a hard time remembering that it's plus in between, and then the difference in y value. So y2 minus y1. Oh, and I'm sorry, I forgot my squared here. There should be a squared here. Make this long enough to cover the whole thing, and there's a squared here. Okay, so it's change in x squared plus change in y squared. All right, that's under the radical. So now that we've reviewed these concepts, let's go on to, let's see here, this first example. Okay, and there's an applet to go along with this, so I would encourage you to log in, or you can just watch my demonstration. But if you want to log in and play along, so we have residents of an island, so 4 kilometers from shore. Okay, so they're out here on this island. Okay, so there's their island. They're 4 kilometers from shore, and they need to get power from a power station that's 10 miles down the beach, or not miles, kilometers, sorry, 10 kilometers down the beach, units matter. And they have to lay wire so that they can run the wire from this point. And so here's the power station. So I'm going to put a P here for power station. And normally you would just run this in a straight line, right? Under normal circumstances, the closest distance between any 2 points is a straight line. Okay, so we would just do this. But here's the catch. Out here where I just drew this red line, this is the water. Okay, this distance here is the shoreline. It's more expensive to run the wire under the water than it is on the shoreline. All right, so we're going to actually go to the applet where I'm going to play with this. So here we are. Okay, and you can see here that going straight from the island to the power station in a straight line, although that would be the minimum distance, all right, that's $21,500 approximately. Okay, if I said, okay, it's more expensive under the water, so let's get out of the water as fast as we can. All right, so if I went like this and said, okay, just get right out of the water, go that 4 kilometers, and then go from 0 to 10. That is cheaper, right? That comes in at $18,000. Okay, but we've built a lot further in distance. Okay, so maybe we can kind of combine the two. Maybe we can get out of the water faster, but not add so much extra distance. Okay, so if I start to move this point along here, I can see that I am getting cheaper, right? Because the overall distance that I'm building is less, but I'm still getting out of the water faster than I was like when I just went straight went across in a straight line. So if I move along like this, I'm still getting cheaper yet. And now, wait a minute, now I'm going back up, right? Now I'm getting more expensive again. Okay, so here, even though I've got like a lower distance, I have more time in the water, and therefore that's more expensive. So I can see that I've got some minimum around here, right about, yeah, right there, right about here. Okay, so I can see I've got a little bit more than 2 miles down the shoreline that I should cross out of the water to minimize the cost. Okay, so here's how I'm going to find that exact point algebraically. Okay, so I'm going to probably just erase this because I know that's not a good idea. And what I'm going to do is I'm going to do a path, like this black dotted line is going to be my path. Okay, and this I'm going to call X. So I better define my variable. Okay, so let X equal the distance down the shoreline in kilometers. Okay, that I need to cross over onto the shoreline. So let's first of all write a formula for the total distance that I would travel there. So a formula for the distance. What did we do in the prerequisite skills? Right, this is the hypotenuse of a right triangle. What did we say the hypotenuse of the right triangle was equal to? Okay, it was equal to the square root of the sums of the legs squared. Okay, so that's the first part of the formula. And then, so that's the diagonal part of this black line. Now I have the distance going here. So from here to here, it's X. And from here to here, it's 10 kilometers. So what would that straight black line be in terms of X? And I hope you recognize that it would be X minus 10. Okay, so there's the formula for the distance. But it's not the distance that I'm actually trying to minimize, it's the cost. Okay, so now I have to work the cost into my formula. And so it costs $2 per meter. Now remember, X is in kilometers. So if it's $2 per meter, there's 1,000 meters in a kilometer. So that would be $2,000 per kilometer. So it's $2,000 per kilometer for this part of the length, but only $1,000 per kilometer for this part of the length. So I'm going to let my cost function be in thousands. So instead of writing 2,000, I can just write 2, but I'll know my final answer is in thousands. All right, so I'm going to write a cost function, C of X. Okay, so if I go this distance right here, and the cost of building that distance is $2,000 per kilometer, right? Then I would multiply this by 2, knowing that it's in thousands. This gets multiplied by 2 because it's twice as expensive as the other region. All right, so that gets multiplied by 2, and then it's only $1 per meter. So $1,000 per kilometer. So, I mean, I'm going to show the 1 times that just for the consistency, right? I really don't need the 1 in the parentheses there. Okay, so here's my cost formula. So I'm going to make a note here under my let statement. So the let statement is so important. I can't emphasize that enough. So C of X equals the cost in thousands. And that's why I was able to use 2 and 1 instead of putting in all those zeros. So now this is the function that I want to minimize. So now I can go to my calculator. So I'm going to stop share. Actually, wait, hang on a second before I go to my calculator. So hold that thought. I'm going to go back to this. So before I go to my calculator, I want to think about how to set my window. Okay, what are the possible values for X? What could X be? Okay, could X be negative? All right, that wouldn't make any sense, right? If X were negative, X is this distance. Could X be 0? Right, like should I start at 0? If X is 0, then I just come straight down. I actually looked at that scenario, right? Using the applet. X could be 0. That means I just come straight from here to the edge. Okay, that wasn't the cheapest, but it was a possibility. And then what's the maximum value X could be? All right, and I had also looked at that maximum value when I just drew the straight line, right, from point A to point P, and that was when X was 10. So X has to be something between 0 and 10. Okay, so I need to know that in order to set my window. So now I'm ready to go to my calculator. And I plugged this in already for the sake of time. So I encourage you to pause the video, type it in yourself and play along with me. And then I'm going to go to window. And I'm going to type in 0 to 10. And my window's on something crazy. Normally, if I were in my standard window, normally my Y min would be set at -10. And my Y max would be set at, yes, I know that's not right. I didn't mean to do that. My Y max would be set at, oh, I put the minus, wait, clear, -10. And then my Y max would be set at 10. That would be what's normal. I try to just leave my calculator in the standard window unless I realize that's not going to work. Okay, so look at the graph, right? And this is where students say to me, my calculator is broken. Right, I'm staring at the screen, I see nothing. The reason you see nothing is you're not in the right window. Okay, the graph is there, but it's off the screen. So your calculator has this wonderful feature called Zoom Fit. Okay, it's number 10, it's 0 here, Zoom Fit. And if I select that, what it does is it automatically adjusts the Y values to fit whatever X you inputted. Okay, so it gives you the Y value so that you can see the critical features of the graph within the domain that you selected. Okay, if I look at Y equals now, or I mean, I look at window now, I can see my Y is between 16 and 21. So that's why I couldn't see it before. My Y went from 0 to 10 and it needed to be larger. Okay, so now I'm looking at the graph and I want to know when this cost function is at a minimum. So I do my second calculate and I select min. And so this key has been very important to us in the last couple of weeks. We've done intersections, we've done zeros, we've done maxes and mins. So I have to mark off my left bound. Some calculators call it lower bound and upper bound, in case yours is saying something different, but same idea. And then right bound, so just make sure I'm to the right of it. And I see 2.3 and then Y is 16.9. So that's why my let statements are so important, is now I have to go back and interpret what I see on the graph. So I come back to this problem and I say, okay, well, what is X? X is the distance down the shoreline in kilometers. Okay, so in order to answer the question, so I'm going to use a text box. so that I can write out my answer. So I need the distance down the shoreline is 2.3 kilometers to minimize the cost of the project at, and so y, right? Y is my cost function, right? C of x is my y, okay? And it's in thousands. So then I have minimized the cost of the project at this value of 16.9 thousand. All right, so a lot of stuff going on here. I think we already need to take a break before we go on to the next problem.